Okay, welcome again to Advanced Chemistry 2 with Pastor Dan. We're going to look today at equilibrium. Now, you remember last year, we talked about equilibrium in a very quick, basic way when we talked about solutions. So we're going to take it in more depth this time and make sure we understand it more directly. Equilibrium reactions, again, are a chemical reaction with the opposite reaction occurring at equal rates. Now, that does not mean they're the same value. That means they reach a point of dynamic change. Now, in an equilibrium reaction then, there is my equilibrium symbol, and the values there we have. When we do that, we have what we call last year KEQ. We now identify that as K sub C for concentration. So we take the products, raise them to their exponents, divide by the reactants over their exponents for the concentrations, and that's Kc. We also can do what we call Kp, the equilibrium product of pressure, and take the pressure of each of those raised to their exponents, divide by the reactants pressures, divide by their reactants. So let's take and do one. Oh, before we do that, let's make sure we talk about the Haber reaction. Haber reaction is important because it was the first equilibrium reaction that was ever discovered by a German scientist named Haber. It's a synthesis of ammonia. So let's use that one. Determine the equilibrium product constant for a reaction with pressures of 1.225 atmospheres of nitrogen, 3.667 atmospheres of hydrogen, and 0.8996 atmospheres of ammonia. So again, there's our reaction, and we balance it because it has to be balanced. So we're using pressures. So we're going to do Kp. Kp is going to be my pressure of ammonia divided by my pressures of nitrogen and hydrogen, and we're going to square the ammonia, and we're going to cube the hydrogen pressures because of the values we have. Plug our values in. We have 0.8996 squared equal divide by 1.225 equal divide by 3.667 cubed equal. When I do that, I get 0.01340. And remember, KQs do not have any units. They're just a number. All right. Now, remember, if Kc is less than 1, that means it's reactant favoring equilibrium. So we have more reactants and less products. The reaction isn't moving as quickly or completely to products. If rather it's greater than 1, then it's product favoring reaction, so the opposite can take place. Now, is there a way we can find the relationship between there? Yes. We use our old friend Pivner, PV equals nRT, ideal gas equation. If I solve for pressure, we get N over T over V. Now, if I move those over each other, N over V moles over liters, that's a unit of molarity. Now, remember, Kc is expressed in molarity, so I can pull all those out of there, and I get a relationship between Kp to Kc, that Kp is equal to Kc parentheses RT, because I pull those out, raised to the delta N. Now, what does the delta N mean? We take all the coefficients of the reactants and add those together and subtract them because it's division of exponents by the values. Let's show more specifically how that works. So for the equilibrium reaction of nitrogen dioxide and chlorine for nitrogen triiodide and oxygen goes, determine the equilibrium product constant for the concentration. If the pressures of the gas at 31.98 degrees Celsius are as follows: 0.9885 atmospheres of NO3, 0.8766 atmospheres of Cl2.
That's NO2, and that's nitrogen trichloride, I'm sorry.
And 0.1223 atmospheres of NCl3, and 0.09876 atmospheres of chlorine. All right, first we need is a reaction.
Oxygen.
Balance. So we're going to write our Kp expression. Kp is my products, NCl3 squared, O2 squared, divide by NO2 squared, NCl2 cubed. Put our values in. We ran that through the calculator, so take and pause if you want to do the calculations. When you do, you should get a Kp value of 0.0001943. Now, we said that Kp is equal to Kc times RT over delta N, and we're looking for Kc here. So Kc is going to be Kp divided by RT. Now, Kp, we just found out, 0.0001943. R, my constant, is 0.0821 because I'm dealing with atmospheres. My temperature is 304.98. Convert temperature from Celsius to Kelvin, add 273. And now we have 2 plus 2, that's 4. And 2 plus 3, that's 5. So 4 minus 5, algebraically, when we have exponents, we subtract them. So my delta n value is -1. So if I take 0.0001943, divide by parentheses, 0.0821 times 304.98, parentheses raised to the -1, equal, I get an answer of 0.04865. That's my KC value.
0, sorry.
All right. All right, let's try another one. Determine the equilibrium product constant for pressure. So then we're trying to find Kp in kilopascals. We have the pressure there. If for the Haber reaction, remember going back to the Haber reaction, the concentration of nitrogen is 0.1122 molar, concentration of hydrogen is 0.3366 molar, and the ammonia concentration at 22.35 degrees Celsius is 0.03339 molar. Okay, Haber reaction again. Remember, that's balanced. So for Kc, that's my expression. Plug our values in, I get a Kc value of 0.2606. Now we said Kc is RT to the delta N, we want this for kilopascals. So we're going to take 2.606 we just find, we use 8.31, it should be 31, times 295.35, and when we do that, we're going to get 0.000004322. 1, 2, 3, 4, 5, 6 zeros, 4322. Awesome. All right.
Actually, 7 zeros, sorry.
Hopefully not too bad. Now, what else can we do? Or express it that way. All right, what else can we do? Calculate the concentration. Now, we can do like we did last year and find the concentrations. So here's my reaction, balanced. My Kc, now remember, I don't include carbon. That's the reason why I want to do this also. Carbon's a solid. We can't do concentrations of solids. So plug our values in. I know oxygen. I know, let me ask you if I'm looking for oxygen. I know carbon dioxide. I know Kc. So plug those values in. When I do, I get a concentration of 21.11 molar. Massive. Again, that's a review from last year. Hopefully not too bad. All right. Lastly then, let's do this one. I want you to pause the video, determine the equilibrium product constant for the concentration, so we're calling Kc, percent nitrogen trioxide from its elements at equilibrium. The pressure of nitrogen trioxide is 0.3455, the pressure of nitrogen is 0.005567 atmospheres, the pressure of oxygen is 0.0167 atmospheres times, and there's temperature. So pause the video, work through that. Any question, let me know, ltswpd@gmail.com. Like, subscribe, share. All right, I'm just going to show the answer. Here we go. And the answer is right there. That's my Kc I find. And that's what Kp, rather. And that's my Kc. All right, not too bad. Hopefully you got it. Take care. God bless. Bye.